Students, transmission impairments की बात चल रही है. We discussed attenuation, we discussed distortion. Now we are going to be talking about noise. Students, noise, any kind of noise corrupts our signal. Noise can be of multiple forms. We can have thermal noise, we can have induced noise, we can have crosstalks, we can have impulse noise. But any type of noise, it corrupts the original signal. Thermal noise, for example, it can be due to the motion of electrons in the transmission medium. Students, induced noise, it can be if your transmission medium is close to things like motors, that disturbs, that creates the noise. Then you've got crosstalk. If there are two wires close together, then that creates noise, which is called crosstalk. Impulse noise is another form of noise, which is it happens when a spike is created, and the spike can be a voltage spike can be due to lightning or any other catastrophic reason. So noise is our third source of transmission impairment, which disturbs our signal. Let's go to the slide and discuss this in further detail. Students, as you can see on the slide, we have got original signal which is transmitted. We have got a noise or an extra signal. Let's suppose it's transmitted because of thermal noise. And when these two signals meet, we receive something at point 2 or the destination, which is not an exact replica of the originally transmitted signal. Now, students, एक related concept of a signal to noise ratio. Students, signal to noise ratio is the ratio of the average signal power or average signal strength divided by the strength of the noise or the power of the noise. In both the cases, we take average values because these two quantities, they keep on changing their values. So we always assume that we have got average values. Once again, let's go to the slide and discuss these in further detail. Students, as you can see, we have got two cases. One in which we have got a high signal to noise ratio, the top one. And then there is a second one where we have got the low signal to noise ratio. So as you can see, the amplitude of this signal, input signal in the first case, is higher than the amplitude of the second one. Signal strength is more in the first case as compared to the second one. We have got noise and we have got noise here. And what we receive on the receiving end is a signal plus noise and signal plus noise. But in both cases, this is not an exact replica of what we transmitted. So students, signal to noise ratio is nothing but a ratio of your signal strength or your signal power divided by your noise power. So essentially, what you're doing is you are creating a ratio, or you're finding out a ratio of what is wanted and what is not required, unwanted or not wanted. Students, a low SNR means that our signal is more corrupted. A high SNR means that our signal is less corrupted. And you can compare the two. The top one, which is high signal to noise ratio, is still a slight replica of what we transmitted. But in the second case, there is no way this signal can be recreated or can be reproduced to what was originally transmitted. Students, before we leave this SNR topic, we need to find out, how do we calculate SNR? Now, because SNR is a ratio of two powers, we describe or we represent that by using the units of decibels. So SNR in dBs is equal to 10 log to the base 10, the actual ratio that you have calculated. So this signal to noise ratio, it needs to be converted into decibels using this formula right here. Students, we'll look at a couple of examples in which we have to calculate this signal to noise ratio. In the first one, the power of the signal is 10 milliwatts and the power of the noise is 1 microwatts. Both are powers, the units are watts. Students, we need to find out the signal to noise ratio and the signal to noise ratio in decibels. Students, how do we do that? In the first case, our SNR is equal to 10 milliwatts divided by our noise power, which is 1 microwatt. If you do the maths, this comes out to be 10,000. Students, as I've just explained it to you, to find out this SNR in dBs, what we do is we convert it into the dBs. 10 log to the base 10 of 10,000, which is equal to 40 decibels. Our signal to noise ratio is in decibels. Students, let's look at another small example. The value of SNR and SNR dB for a noiseless channel, a channel in which the noise is equal to 0. This is not a real life scenario. So there is never, we have not come up with a channel at all which has got a noise of 0. But let's try to find out the SNR. In this particular case, we have got signal power, whatever that power is, divided by the noise power, which is 0. And therefore, our SNR is equal to 10 log to the base 10 of infinity, which is also equal to infinity. Not real. So we cannot have a noiseless channel. There has to be some sort of noise, whether it's heat, whether it's induced noise, impulse, or whatever it is that we'll have in our transmission medium.